It's time to start. Thank you everyone for being here for this afternoon session. So the first talk of this session will be given by Nadeeb Al-Rashid, who is currently assistant professor at the University of Leeds. And he will tell us about importance sampling for Makin-Vlasov stochastic differential equations. Nadeeb, the floor is yours.
Thank you, Shihab, for the nice introduction. I hope my voice is clear to you. You hear me correctly, right? Okay. So thanks again, Shihab and Raoul, for the invitation. Today, my talk is about our recent work on importance sampling for the context of Makin-Vlasov SDEs. And this is a joint work with Raoul Tamtoni, Sham Mohan, who is a PhD in RWTH Aachen, and Abdul Latif Haji Ali. So if you have any questions, please do not hesitate to stop me at any time. Okay, let me directly start with the definition of a Makin-Vlasov SDE. So it is an E to SDE where the drift and the diffusion coefficients depends on the law of the solution itself, which we denote by mu t here. So mu t is deterministic law, but it's unknown. W is a d-dimensional linear process with independent components. Kappa 1, kappa 2 are called the kernels. And mu t, as I said, is the PDF of x at time t. And x0 is just the initial state, which is this, sampled according to this law mu0. So our objective is to estimate this quantity here, where G is a rare event observable, and G applied to the solution of the Makin-Vlasov SDEs at the final time t. So for example, G can be the indicator function that x is larger than k, and this corresponds to the rare event probability. Probability that x, the solution of the Makin-Vlasov at the final time t, is larger than a threshold k. Okay, if we write the probability density function of x at time s, given that we start at time t at the state y, then this is the Fokker-Planck partial differential equation. So then we get this nonlinear integral differential PDE with non-local terms because of the dependence on of the drift and the diffusion on the law. So this PDE is computationally expensive to solve when we have a high dimensional problem, when D is large. And even for D equal to 1, conventional numerical methods do not control relative errors, which is the quantity of interest in the rare event regime. Okay. So now I'll tell you how we can approximate this Makin-Vlasov SDE by this system of p-coupled E to SDEs. So these are standard p-coupled E to SDEs, each in dimension D. So the idea is just to approximate this deterministic law by this empirical law, which is given by this average of this Dirac centered at the state of the particle at time t. So if you apply this approximation, we get this standard SDE. So this p-coupled standard SDEs, each with dimension D. Okay, W here are mutually independent linear processes, and x0 from p equal to 1 to p are IID samples from the initial distribution. Okay, so if we again apply, look for the Fokker-Planck for this, for the distribution of this xp from p equal to 1 to capital P, given this that at time t we are at state y, and for convenience we just we write it in d equal to 1, then we get to linear PDE. This is linear, but in p times d dimension. So it's computationally very expensive to solve numerically. And this, of course, motivates the use of Monte Carlo methods to approximate our expectation. So before going to the Monte Carlo method, I just give some examples where this particle system, this interacting particle system can be applied. For instance, it can be useful to model pedestrian dynamics or mathematical finance as well. And also, when we go back to this particle system, and under some regularity condition, if we let P, the number of particles, goes to infinity, then we get that each SDE will converge to the mean field, which is the Makin-Vlasov SDE. Okay. Okay, so I present here the running example that we will use later for the numerical simulation. So this is a 1D example. It's brought from statistical physics, and here it's a system of p-coupled oscillators, and the dimension here is 1. So also the diffusion is constant, but we have this kernel which is a sinus, non-linear kernel. Nu p is RIAD sampled from this distribution x0. We choose it to be normal, and of course nu p, x0, and w for all particles are mutually independent. And in this kind of example, we are usually interested in computing this total synchronization, which is given by the expectation of the cosine of the solution of the Kuramoto model at final time t, and this is for the cosine and also for the sine as well. Okay. So what is the objective of this work? We aim to construct an efficient Monte Carlo estimator A of this quantity, of this expected value, such that the probability that the relative error, being less than a given relative tolerance, holds with high probability. And of course, we need to satisfy this with minimal computational work. In our work, we will consider 3 types of rare event observables. The blue one is just the probability. It's the probability of rare event. And the second one are just a modified version that we will need later when we will work with multi-level and multi-index Monte Carlo. We'll come back to these choices in the numerical results. Okay, the question now, why do we need importance sampling? The answer is quite simple. So for instance, if we consider G to be the indicator function, that X is larger than a sufficiently large threshold K, then this corresponds to this rare event probability here. Okay. And to satisfy the relative error toll, like let's say 5%, then from the application of the central limit theorem, we know that the number of required samples should be approximately equal to this. And most importantly, it is inversely proportional to the quantity of interest. So if this probability is relatively small, then we need a substantial number of samples to meet a given accuracy requirement. Okay. So this motivates to use variance reduction techniques, and in this work we will use importance sampling, which is very common technique that can be used to reduce the variance of Monte Carlo estimators. Now, before talking about importance sampling in the context of Makin-Vlasov SDEs, we start with standard SDEs, and I will show you how we can apply importance sampling, and then we try to extend it to Makin-Vlasov SDEs. So here we consider this standard SDEs, SDE with drift B and diffusion sigma, and W of T is just d-dimensional linear process with independent components. And again, the aim is to compute this expectation here for a given observable G. To make the change of measure easier, we start with the discretized version. We start by discretizing the SDE with Euler-Marioма time discretization, which is given here, where epsilon are IID, normally distributed, with mean vector 0 and covariance matrix, the identity, okay? And then the change of measure that we consider is to just, instead of sampling this Gaussian with 0 mean, we make a shift to this Gaussian. And the shift is given by the square root of delta t times this zeta. And this zeta is deterministic Markovian control because it is a deterministic function of the current time and the current state of the system. Okay? We also compute the likelihood factor for the nth step, which is just the ratio between 2 Gaussians with different means. And after defining the likelihood at 5, the Monte Carlo, importance sampling Monte Carlo estimator can be written at the expected value of G of this modified process times the likelihood ratio. And this Y and zeta satisfy this equation with this additional term, which is coming from the change of measure. So it's the diffusion times the control. Okay. Any question? Is it clear? Okay. Now the question is how to choose this control zeta from n equal 1 to capital N. So the idea is just to try to minimize the variance of this importance sampling estimator, or equivalently, we minimize the second moment because we know that importance sampling is an unbiased estimator. So we try to find this zeta such that this second moment is minimized. And then by taking the limit as n goes to infinity, we can get this continuous time formulation. So we can define this second moment, which we call cost function in the terminology of optimal control, with multiplicative cost. This is the difference between what our setting and standard optimal control problem, where we have an additive cost function. So this is basically the second moment, which is equal to the expectation of the observable square applied to this controlled SDE times the likelihood factor square, and then we condition that the SDE at time t is equal to x. This is for the purpose of defining later the Hamilton-Jacobi-Billman for the optimal control problem. Now we define also the value function. So what is the value function? It is just the minimum over all possible controls or over all admissible controls of the second moment of the estimator. And this minimization should be performed under the constraint that this y zeta t solves this controlled stochastic differential equation. Okay, so actually this is basically the same as the Grizanov theorem, but I wanted to give you a small proof how to get to Grizanov theorem starting from discrete time. Okay, so for this multiplicative structure, we were able to find the dynamic programming lemma. So basically, we relate u at time t x to u at time t plus delta x. So this so knowing the final condition, we know that the u at final time is equal to the observable square. We can try to solve this dynamic programming by going backward in time, for instance. Okay, but from this dynamic programming lemma, what we did, so we expand the exponential and we use Ito here and take the limit as delta goes to 0 to get this Hamilton-Jacobi-Billman PDE for this important sampling problem. So we assume here some regularity as usual, and we let gamma related to u through this formula. So u is equal to the exponential of -2 gamma. Then we can show that gamma satisfies this nonlinear Hamilton-Jacobi-Billman PDE here. And also the optimal control, which minimizes the second moment, are related to this value function, to this gamma through this formula here. So if we solve this this PDE and we get the optimal control can be deduced from this formula here. Okay. So also we can easily prove that using this optimal control, we get an estimator with 0 variance, provided of course that G, the observable, does not change a sign. And to see this, the proof is very easy. If we denote by, if we do this change of variable, U equal to V squared, then we can show that V solves the Kolmogorov backward equation. So what does it mean? It means that the second moment is basically equal to the first moment squared, and then it means that the variance is 0. Okay, so as I said, this is exactly the Kolmogorov backward equation, but we will not solve this with high precision. So we'll try to roughly solve this PDE here to get an approximation of importance sampling, and then feed this importance sampling parameter into Monte Carlo to get an accurate result. So this, we will not solve this PDE very accurately. We just need it. We need to find a rough approximation to get the control out of it. So it's important to mention that our approach basically leads to the same result as this paper of Hartmann, but in that paper he used the Dungsor-Varadhan variational principle. But in our setting, we started from the minimization of the variance. But at the end, both approaches converge to the same thing. Okay, now we move to Makin-Blasov SDEs. What are the challenges here? As you remember, the drift and diffusion of the Makin-Blasov SDE depend on the solution, on the low mu t, right? So any change in measure will change the drift and the diffusion coefficients. Which, I mean, it's not easy to just do importance sampling directly to the Makin-Blasov SDE. If we try to use the particle system, so we approximate the Makin-Blasov SDE by this set of p-coupled SDEs, which are standard SDEs. The problem that in this case, we'll get p times d dimensioning problem again to solve to get the control. So this is very expensive. So what's the idea? The idea is based on this decoupling approach developed by Dorais and Peter Tenkov. So the idea is to convert this Makin-Blasov SDE to standard SDE. And then once we have this standard SDE, we can apply importance sampling to it, as we have seen before. How to do this? So we have two steps in this framework. So we start first by approximate the law mu by the empirical law, as before. So we consider this particle system to get the empirical law. And then, given the empirical law, we define this decoupled Makin-Blasov SDE. So this is basically a standard SDE given the law. So this green particles here are given in the second step. So if we assume that we have the law, then this is a standard SDE, and then we can use importance sampling for this second step. Okay, so let me go back. So this W bar here is again a Wiener process in RD, and is independent of the Wiener processes that are used in the first step to get the particle system. X0 bar is the initial distribution, some initial states sampled from this distribution, and again is independent of the all other initial, all other initial states in the particle system. And also under some regularity, also that when P goes to infinity, this SDE here will converge to the Makin-Blasov SDE, because this sum here, so in this sum here, we'll get the integral of K2 times the rho, the deterministic law. Also, as I said, it's very important to remember that this SDE that we defined in the second step, it's a standard SDE given the realization of the law. So you can think of an SDE with random input, with random coefficients, okay? So using this decoupling approach, we can basically approximate our expectation here by this nested expectation. The inner expectation is the expectation with respect to P bar, and P bar is just the randomness induced by the Wiener process in the decoupled SDE for a given law. And then we get an outer expectation. This is with respect to the randomness generated by the law. So, and this nested expectation motivates the use of double loop Monte Carlo to estimate our quantity of interest. So this is basically written here. So without going into much details, of course, we use Euler discretization to discretize the stochastic particle system and the decoupled SDE. And this is our double loop Monte Carlo estimator for this setting. So M1 is the number of times we generate the empirical law, and M2 is the number of times the number of samples for the from the SDE, from the decoupled SDE. Okay, I denote here W here to be the randomness with respect to the Wiener paths and the initial conditions in the particle system, and W tilde is just the Wiener paths in the decoupled SDE. Okay, now what's the idea? Now the idea is to apply importance sampling only to this decoupled SDE. So by thinking again that this decoupled SDE is a standard SDE for given realization of the law. So basically what we did, we decouple the approximation of the law from the use of importance sampling. And once we have the law, we use the same formulation as I showed to you for standard SDEs. We have this the controlled SDE, and then also can define the value function, but the difference here is that the law is given, and we can get the dynamic programming and also the Hamilton-Jacobi-Bellman equation as before. These are stated here. So just a small remark that now in this case, the control will depend on the particles in the particle system. So you can think of a control that is random here. So if you change the empirical law, the control will change. Now, how to couple this double loop Monte Carlo estimator with importance sampling? The idea is simple. It's the same estimator, but we have to add this likelihood ratio term. And the likelihood ratio is again given by the Girsanov theorem. Now, the question now is how to choose the parameters in the double loop Monte Carlo estimator. So how to choose the number of particles, how to choose the number of time steps in the Euler-Maruyama discretization, how to choose M1 and M2, the number of samples in the outer and the inner loop. For this, we need to do a work error analysis. So we start with the error. So again, remember that we would like to achieve this, that the probability of the relative error being less than a given tolerance is larger than 1 minus alpha. So we first split the relative global error, we can call it like this, to relative bias and relative statistical error. And a sufficient condition to ensure that the first equation is satisfied is to bound the relative bias by theta times the relative tolerance, and to ensure that the statistical error is less than 1 minus theta, the relative tolerance, holds with high probability. If theta is a number between 0 and 1, for our case, I think we choose it 1/2. But if you ensure that these two equations are satisfied, then this is sufficient to ensure that the first one is satisfied. Okay, let's start with the bias. For the bias, we can split the bias into two terms as well. The first term is only function of P, and we call it the decoupling error. This is coming from approximating this Makin-Vlasov by this decoupled SDE using the empirical law. And the second term is the time discretization error coming from the Euler discretization. And our assumption, without entering too much into details, is that the bias will decrease with rate -1 in terms of P and N. And here we verified this numerically for the case of the Kuramoto model. And for the case of G of X equal to cosine of X, we see that we got the assumption is numerically satisfied. Okay, what about the variance? From the central limit theorem, we can approximate the statistical error by this confidence constant times the square root of the variance of the estimator. And we can compute using the law of total variance, the variance of this estimator. And it is basically given by 1 over M1 times the variance of the conditional expectation plus 1 over M1, M2, the expected value of the conditional variance. Okay, so our assumptions is that the second term is just big O of 1, but the first term will decrease to 0 because as P goes to infinity, the random empirical law will converge to the deterministic law. And then we get convergence to 0. And we claim that this convergence happens with rate -1 in terms of the number of particles. This is again verified here numerically for the Kuramoto model. We have this big O of 1 conversion. There is no convergence here. It's big O of 1 for the second term, and we have convergence of the first term with the correct assumed rate. Okay, and here also we use G of X equal to cosine of X. Now we talk about the work. So the work of one realization of the particle system is N times P squared. Why? Because we have P couplet SDE, and we have this average. And if I go back, it's almost here. We have to compute this average for each particle. Then we have P squared first, and times N because of the Euler discretization. And then we have also the cost of solving the PDE. and the cost of one realization of the decoupled SDE, which is P, again, because of the empirical mean, and N because of the number of time steps. So this is the total work. And of course, we don't do anything. There is a problem here because we need to solve the PDE M1 times, and this is too much. So what we propose is to try to solve the PDE offline once, using some fixed number of particles and fixed number of time steps. So now, basically, our control is not random, it's deterministic. And this is an approximation that we make to reduce the cost, but as you'll see later, this reduces the variance, and this is good. I mean, we got a substantial amount of variance reduction using this technique. So with this, we modify basically the work. So we have this offline cost of solving the PDE that we would neglect, and the work is basically equal to this term now. Here, I want to present the algorithm. So we first generate the empirical law using P bar and N bar. And then given the empirical law, we solve the PDE once outside. And then we do our double loop Monte Carlo. So we generate M1 realization of the law. Given the law and the control, we generate for each realization of the law, we generate M2 samples of the decoupled SDE. And of course, we compute the likelihood. And at the end, we do this M1 times to get this double loop Monte Carlo estimator. The idea is quite simple. Now for the work, for the parameters, we need to solve this optimization problem. We minimize the work that I have shown to you, subject to the bias constraint and the statistical error constraint. This constraint should be satisfied. And what we achieved that we solved this optimization problem. We found the optimal P, N, M1, and M2. And we found that this double loop Monte Carlo estimator has complexity equal to tol minus 4. So the important remarks is that in the original paper of the decoupling approach, M2 was chosen equal to 1. So there is no double loop. But if we choose M2 equal to 1, we get tol minus 5 complexity instead of tol minus 4. This is to justify that this double loop is really important. We got the same complexity as the work of Raoul and Abdul Latif. We get tol minus 4 complexity, but we incorporated importance sampling in this framework. So the constant in front of this tol minus 4 has been reduced substantially. Okay. Now we will try to extend this single level approach to the multi-level approach. So with this, for this, we define this hierarchy in terms of number of particles and the number of time steps. Tau here is, we choose it to be equal to 2 in our simulation. And for ease of notation, we call G to be the exact, to be the exact observable applied to the exact solution. And GL is the observable applied to the our approximation with PL number of particles and NL number of steps. The idea of this multi-level is just to write the expectation of G at the finest level of this telescoping sum. And then what we do is to approximate each of these expectations using our double loop Monte Carlo estimator. So this is the multi-level double loop Monte Carlo estimator, which is given here in this expression here. So this calligraphic GL minus 1 will be discussed in the next slide. It's basically chosen to ensure a high correlation with respect to GL, but at the same time, its expectation should be equal to the expectation of GL minus 1. So again, the global error can be split into bias and statistical error. The bias has been studied before. For this estimator at level L minus 1, we provide two sources of this estimator. The first one is the following. So you get the empirical law using PL particle systems. And then you just take the Wiener passes of the first PL minus 1. And then apply, and then apply, use this path to get the empirical law, and with this we get this GL minus 1. The second one, which is we call it antithetic sampler, is to do the same with the second half, second PL minus 1 number of particles, and then at the end you average these two quantities. Okay, we'll show that this second one will give more better convergence rate. So for the bias, it's basically the same as before. So the convergence is alpha tilde should be equal to 1, because we know that the bias is 1 over P plus 1 over N. So this is expected. For the variance of this multi-level double loop Monte Carlo, we can compute it, and it's equal to the sum from L equal to 0 to capital L of V1L over M1L plus V2L over M1L M2L. And V1L is the variance of the conditional expectation, and V2L is the expectation of the conditional variance. And we denote by W tilde the rate of this decay of this V1L, and S tilde to be the rate of V2L. So for the antithetic sampler, and for this choice of the Lipschitz event observable, we get that W tilde is equal to 2 and S is equal to 1. And here we also derive the optimal complexity for this double loop multi-level estimator. So without entering, I will not enter this in the details, I will just give you one example. So for the Kuramoto and for this event Lipschitz observable, we get, for the naive sampler, for the first sampler, we get W tilde and S tilde equal to 1, both. And hence, we get tall minus 4 complexity. So there is no reduction compared to the single level. But if we use the antithetic sampler, we get W tilde equal to 2 and S equal to 1. And if you plug this in the previous theorem, you will get that you will get tall minus 3 complexity. So we reduce the complexity from tall minus 4 on the single level to tall minus 3 in the multi-level. So this is without importance sampling. So the next slide, we propose a way of incorporating importance sampling within this multi-level approach. So the naive, or the most natural way, is to use the same control obtained in the single level control problem and apply the same control across all levels. Okay, this is the natural extension, I say, this framework. So the intuition is that since this control reduces the single level variance, we can think that it may also, if we apply the same control level N and level L minus 1, at the end we can reduce the variance of the difference. And we'll show later that this will be enough to ensure a substantial amount of variance reduction. So here is the multi-level estimator combined with importance sampling. So again, we start with this telescopic sum, and then we add this likelihood. I mean, we do the change of measure and add this likelihood term at level L and the likelihood term at level L minus 1. So the likelihood is the same as before, and basically we got the same multi-level estimator with the addition that we multiply by this likelihood term at level L and level L minus 1. This is the adaptive algorithm that we implemented. So first, again, you compute the control for a given law, and then before entering to this while loop, we estimate we get a rough estimate of the quantity of interest at level 0, together with an estimate of V10 and V20. And then, as long as the bias is not satisfied, we keep increasing the number of levels. And for each level, we estimate V1L, V2L. We compute the number of samples that we need per level. And we estimate the bias from this heuristic here, and we update our estimator. And we keep this while loop until we get convergence of the bias. Okay? So we discuss the numeric results. So we start with the single level. So we have an indicator function as an observable, and we choose k such that our rare event probability is almost 2.5 10 minus 4. Here we plot the estimator as a function of toll. And here we check that for a given toll, the error that we make is always bounded by the tolerance. And this is should hold because we want this to hold with high probability. So for the global error, we use some reference double loop Monte Carlo value with a very small tolerance, which is 1%. Okay. Now for the, we also plot here the runtime, the computational time we need for Monte Carlo plus importance sampling as a function of toll. And we get, as the theory, we get toll minus 4 complexity. Here we didn't plot the Monte Carlo without importance sampling because it's very expensive. We cannot do that, at least in my local machine. And then we compare here the work estimate, because the work estimate, you can estimate the work without running the algorithm. So, and we see here that with importance sampling, we get a substantial amount of variance reduction, more than 1,000, I think, in this case. Yeah. Okay. Also here, we change k. So we increase k, so we decrease the probability of interest. And we would like to see what is the impact of this algorithm on M1 and M2 together. So this is the without importance sampling, and you can see that the more rare is the event, more samples we need. But with importance sampling, we reduced the number of samples dramatically compared to the case without importance sampling. Okay, for the multi-level, again, we make sure that the estimate of the global error is bounded by the tolerance that we would is bounded by the tolerance, relative tolerance. And here we plot the runtime of the single level and the multi-level. And we clearly see that with the multi-level, we got toll minus 3 complexity as claimed by the theory. Here, we consider the Lipschitz rare event, so it's not a probability, but still it's a rare event problem. And the value is 3.2 10 to the power minus 3. Okay. Also, we do the same with the work estimate, and we see clearly the toll minus 3 convergence, toll minus 3 complexity of the multi-level estimator versus toll minus 4 complexity of the single level estimator. And here, also, we do the same by varying k, actually. So by increasing k, we get more rarer event. And of course, as we increase k, the constant will increase. But this is not the whole story, because with Monte Carlo also, the constant will increase maybe exponentially. I mean, the constant in front of the work will increase exponentially with respect to the threshold. But here, I mean, maybe a nice plot, maybe to do the same with Monte Carlo and see what is the effect of the threshold on the constant. Okay, the last few slides is that we also worked on extending this to the multi-index Monte Carlo framework. So the idea here is that we have two discretization parameters, P and N, and this motivates the use of multi-index. Okay. And for the multi-index, since we need more regularity, we use this modified function to ensure that is smooth enough for the multi-level, to ensure that this first order mixed derivatives are bounded. So very briefly, the idea is that you consider a multi-index in 2 dimensions. Alpha 1 is the index for the number of particles, and alpha 2 is the one for the number of time steps. And we define G alpha to be the estimator. I mean, G applied to the approximation with P alpha 1 number of particles and N alpha 2 number of time steps. And again, we multiply by the likelihood because we want to do importance sampling here as well. And for the multi-index, we, instead of the difference between the levels, we have this first order mixed difference. In our case, in dimension 2, this first order mixed difference is given by this expression here. And here I present to you the multi-index Monte Carlo estimator. So I here is the chosen set of multi-indexes, and M1 alpha is the number of samples in the outer loop, and M2 alpha is the number of samples in the inner loop. And again, for the variance, we just sum over multi-indexes, or all multi-indexes of this V1 alpha over M1 alpha plus V2 alpha over the product of the number of samples. And again, for the multi-index, we need to make some assumptions on V1 alpha and V2 alpha as in the multi-level setting. I write here also the work in the multi-index setting. So here we just, I think I will go to the next slides because it's too much details. The main conclusion is that we were able to get, I think the best complexity in this case is 12 minus 2 using this multi-index, Monte Carlo, plus, I mean, we reduce dramatically this constant to be able to efficiently estimate rare events. Okay, so this is the conclusion. So the important sampling scheme that we discussed for decoupled McKean-Vlasov of SDEs, we coupled it with the optimal control to reduce the variance. We get 12 minus 4 complexity for the single level plus reduced constant, and then we move to 12 minus 3, and then at the end, we got 12 minus 2 with this log term for the multi-index, of course, together with enabling feasible estimation of rare events. So this is the 2 papers that are available that you can check. The third one will appear soon, and these are the references that I have used. Yeah, thank you very much.
Thank you, Nadir, for the nice talk. Any questions from the audience? Okay, then maybe I can start. So the first question, you said that compared to the approach where they did not use double loop, so they have only M2 equal to 1. Mm-hmm. So you gain 1 order of tolerance, but what happens with respect to the constant compared to that case?
Not sure how to answer this, but yeah, I think the main idea is that if we don't make this inner loop, because the inner loop, I mean, it's just one SDE to sample from, but the outer loop is more expensive because it's a particle system. So it is what I want to say here, that since it is cheaper to sample from the inner, from the decoupled SDE, I think it's not optimal to take M2 equal to 1. And I mean, the main motivation of this is that the double loop will tell you that we can get from 12 minus 5 to 12 minus 4. But in terms of constant, I don't know. So what will happen? Not clear.
Maybe I can still ask another question. You only treated cases where you have Lipschitz kind of observable, so but you can also do tricks to handle, I mean, the indicator function, I mean, right? Because otherwise multi-level should suffer, I mean, on that case, right?
I think this is a good question, because if we have the indicator function of the multi-level, things will not work. I mean, we'll not have the optimal rates, so we need to do something.
And then multi-index is much more.
Much more. So, but this is something that we are planning to do very shortly. So.
Okay, thank you. Okay, so if there are no further questions, let's thank again Nadir for the nice talk. So we have approximately 10 minutes to the next talk, so you can take a short break and then come back again.